Okay, so welcome to this seventh doubt clearing session of the course Engineering Thermodynamics. So let me take up the first question for today. So it's uh, in steam table, saturated water temperature table, what is meant by evaporation and what is its significance? Okay, so yes, while we have presented the internal energy, the enthalpy and the entropy, at that time we have seen that we are having one first column for UF which shows the internal energy of the saturated liquid. Then we have nothing but Ug which shows the internal energy of the saturated vapor, and then in the middle we have some column which is nothing but UFG, and we are calling that as Ug minus UF. Okay, and in that UFG it is written that it is nothing but evaporation. So the meaning is, because it represents the change of phase from liquid to vapor. So UF is nothing but the internal energy corresponding to the liquid phase, and Ug is nothing but the internal energy corresponding to the vapor phase. So that's why Ug minus UF is nothing but it represents that what amount of change of internal energy, or if I take the corresponding enthalpy, then what amount of change of enthalpy or what amount of change of entropy has happened while our medium has transformed from liquid phase to complete vapor regime. Okay, so that is the only meaning of this. Is it okay? Rijul is
Yes, sir.
okay. Then next question is what is the need of thermodynamic surface while we have already plotted the graph between the three parameters? Yes, we have separate two-dimensional diagrams, but obviously if say we want to visualize on a three-dimensional plot that how the variation of pressure, temperature and specific volume combinedly takes place on our property diagram, common property diagram. For that purpose, actually, we try to plot the PVT surface. Okay, as such, there is not much requirement of PVT surface. It is only for the sake that whatever the properties, measurable parameters we are having, while we will be presenting these measurable parameters, then how these will be appearing. That's it. That is the whole idea. Is this okay? Amrendra.
Yes, sir.
Okay, next question is, how is value of phi equal to 2 in saturated state? Question number 2 is, in steam table for calculation of enthalpy, what value of P is used and what is F for air? Okay, so now I'll take one by one. The first question is, what is value, how is value of phi equal to 2 in saturated state? So when we talk about saturated state, I have already told you that if particularly, let me once again show with the help of TV diagram. So if I plot TV diagram over here, this will be my liquid vapor dome, and say this is some constant pressure line over here. Okay, so you can see that corresponding to the same value of temperature, say T1, we are having the occurrence of liquid phase also, we are having the occurrence of pure vapor phase also. Okay, so it means if you are only given a same value or single value of either temperature or pressure, and it is told that corresponding to that you are having saturated state, so it clearly means because for the same value of the property we may have a situation of saturated liquid, we may have situation of saturated vapor, or we may have a mixture of liquid and vapor. So that's why at that particular property value, if we are calling that state is saturated, it means at saturated state there are chances that both the phases can exist. So because of that we are taking the value of phi equal to 2. Is it okay?
Sir, how there will be a mixture in saturated state? Saturated state is the state in which only liquid or vapor will be present.
Yes, so
How
that's
is the
what.
mixture present?
No, so that's why while we are taking the mixture, for mixture we are defining one additional parameter x. Okay, so when we are saying saturated state, then only we are pointing to either liquid or vapor. And what I am saying, at the same temperature and pressure, we may have mixture situation also additionally, but while we will be having mixture situation, we have to use some additional parameter. Okay.
So, sir, in this case, I will be 1 by 2,
Why
either
to?
liquid or vapor.
Yes, liquid or vapor. Yes, that's why. Either it can be saturated liquid or it can be saturated vapor. Is this point clear?
So, sir, phi should be 1.
No, 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 no. Phi, see, phi is not the situation that is pointing to a single value, a single phase. Phi is a parameter which is showing that at that particular condition of temperature and pressure, what parameter, what phases can exist. So that is a general statement. So in general, two phases can exist. So because of that only we are coming to criteria that we require only single property after we are actually specifying whether we are having liquid or vapor. Okay, so liquid or vapor specification is actually kind of your state postulate specification, that we are specifying two parameter. First is we are specifying any property, and second thing we are saying that we are having actually we are having the presence physical phase whatever is present, whether it's liquid or it's vapor. So that is acting as a second input to specifying the characteristic of the system. Now is this point clear?
Sir, please repeat as I got disconnected.
Okay, so the response is what I am saying, that at any temperature or pressure there may be a coexistence of liquid or vapor, or there may be any phase, either complete liquid or complete vapor. So both can present. So while we are talking about Gibbs phase rule, we are talking in general about the saturation state. So in general, at the given condition of temperature or pressure, there can be occurrence of liquid and vapor. So that's why we are calling as phi as 2. Now the second point is, if I try to relate it to the state postulates, so as per state postulates we require two independent properties to specify the state. So in case of saturated liquid and vapor, we are only specifying one property. Apart from that, we are specifying that what is the physical state of the substance, whether substance is in liquid phase or substance is in vapor phase. So that is actually acting as another parameter. Another parameter over here is nothing but our physical state of the substance. So because physical state of the substance is already known, so because of that only we are able to obtain the value of other property by just knowing a single parameter. Now is this correct? Is
Yes,
this
sir.
okay? So should I take up your next question then?
Yes, sir.
Your next question is, please explain the Gibbs phase rule for mixture of liquid and vapor. So that's what. Why now if you see, actually the mixture of liquid and vapor is also coming into the saturation regime only. So that is in between two saturation lines. So that's why for this mixture, though as per the Gibbs phase rule, we are having the situation which specifies that only one property will be able to determine its property, but already I have told you that Gibbs phase rule and state postulates shows some issue while we are having actually phase transition and we are having the coexistence of two mixtures. So apart from the parameters specified by these general rules, we require one more additional parameter to specify the state. Is it okay?
So that means that the one that we obtained from Gibbs law, the Gibbs phase rule,
Yes.
is this the number of extra parameters that we required?
This one, no. So this one basically what we are trying to say, we are trying to relate this parameter as minimum requirement. Okay, apart from that, now if we have situation where we are having mixture, then obviously one additional we will be requiring for phase transformation. Okay.
Sir, but in formula we consider the phase and we are again telling it a parameter. So in formula that we made for that, how many parameters do we required? We considered the number of phase which are existing in the system,
Yes.
and while calculating it again, we are considering the phase as a parameter.
No. So what I am saying, while we considered in general formula, that was particularly corresponding to the saturation state. Okay. So when we are talking about saturation state, we only refer to the saturated liquid line and saturated vapor line. And mixture we treat differently, though it is in between the saturation states only, but generally because how much amount of liquid is changing into vapor, that we are not knowing. So for that we require actual physical state of the system. Moreover, I have already explained you, because while we define any property for the mixture, that doesn't represent the physical state of the system. Okay, so for example, if for the mixture I have some specific volume V, that doesn't mean that that specific volume is everywhere same. That is nothing but an number which is a representative of the bulk property of that system. Is this point clear? So that's why mixture is actually treated completely different than our normal system.
So, sir,
Okay,
in
sir.
finality, we would say that state postulates and Gibbs phase rule do not comply with each other for a mixture of liquid and vapor.
Yes. For mixture we require like additional parameter which has to be considered. Okay.
So we should, so we would, for a mixture, we would always consider the state postulate only.
No, yes. So what we will be doing basically, kind of you can consider that state postulate is always true for every system, and for a mixture, the requirement of additional parameter is being specified by the Gibbs phase rule.
So, sir, in saturated, we only require one parameter, and one is already with us because it is saturated.
Yeah, because we are knowing the physical state. Okay.
Yes, sir. And physical state is a parameter.
That's kind of parameter we can consider, because that also one has to first see that, okay, what is the physical state. So obviously if I want to define any property there, I can define corresponding to that physical state.
Okay, sir.
Sir, so pressure, temperature, volume, these all can be the parameters
Sorry.
for degree of freedom. So,
Yeah.
like, if we find the
Any intensive property can be used to specify the states. So in the morning you might have seen I have given you an example where I told that if I give you question like I have saturated liquid state and I have internal energy of 170, you determine the saturation pressure. So parameter can be, it can be internal energy, it can be enthalpy. Any intensive property can be used to specify the state. Okay. But yeah,
yes, sir. Thank you, sir.
practically while we will be using, practically it is easy to measure pressure, temperature and volume rather than measuring the internal energy and enthalpy. So that's why actually practically what we do, we try to always represent the parameters in terms of represent all other properties in terms of pressure, temperature and volume only, which can be easily measured. Okay.
Yes, sir.
Okay, question number 3 of Lavis is what is F for air? Okay, so let me now take up this question. So now if I write F for air, then for air now we'll be having like different composition. The first thing is air I am considering as a pure substance, So it means I'll be considering air as my single component only. Okay, so I am considering air as a pure substance. It means air is nothing but a single component. It is having same chemical composition everywhere. So C will be 1, and air, what we are having, that is only in gaseous phase. So air is only in gaseous phase. So because air is only in gaseous phase, so we will be calling this air as having phase phi equal to 1. So for F for air, you will be finding as 1 minus 1 plus 2. Okay, so it means two parameters will be required to specify the state of air. However, so this is particularly true for dry air, when we are having dry air. If we are having moist air which is nothing but mixture of moist air is mixture of water and air. So mixture of water vapor and air. So when we are having water vapor also in our air, during that time number of components now will be 2, and number of phases, because water will also be present in the vapor phase. So air will also be in gaseous phase and water will also be in gaseous phase, vapor form. So number of phases will be equal to 1, and for moist air we will be finding our degrees of freedom as nothing but 2 minus 1 plus 2, and it will be 3. Okay, so is this point clear?
Sir, why is phi 1?
Because while we will be having moist air, the meaning of moist air is we are having water vapor present. So water is present in the air in vapor form only. So both air and water are in gaseous phase. Okay, so that's why our value of phi is equal to 1.
Sir, we don't consider water vapors as a component of air.
So for moist air, we are not considering it at the moment. So that's what, like if you want to consider it as a component of air, then we will be saying that our air is only dry, and if we are including the water vapor in air, so in that case we will be calling it as moist air. So that is up to you. For example, when we will be talking about the applications of air conditioning, which is a part of applied thermodynamics, so we always say that in our room we have to maintain some humidity level. For example, 22 degrees Celsius is the temperature which is required for human comfort, and relative humidity of the air should be 56%. Okay, so that is a parameter which is very important in controlling the quality of the air. So that's why we may change the moisture content of the air depending upon the requirement. Many times we are having some process industry where we have to control the moisture level in the air. So generally, because artificially or naturally the moisture content of the air varies, so that's why dry air and moist air are treated separately. Okay.
Okay, sir.
Sir, what was the answer of second part?
Second part, okay. So what I told you, that while we are talking about the mixture, under the condition of mixture and state postulates, what we are doing, sorry, under the condition of mixture, what we are doing, whatever the number of parameters we are getting, apart from that, we have to provide one additional parameter in order to specify the state. Okay, because whatever the value of property we get, for example, specific volume, or for example, internal energy of the mixture, that is not a homogeneous property everywhere within the mixture. Rather, that is a number representative of the state of the system, which is taken based on the weighted average. Okay, so that's why we require one additional parameter to specify the state. Is this point okay?
Yes, sir. And sir, in the steam table, when we find the enthalpy,
Yes.
what was the value of pressure used?
What is the value of
Pressure.
pressure? Oh, pressure will be the corresponding pressure state.
That saturated pressure.
It will be, yes, saturated pressure.
Okay, sir.
Then next question is, why do we have a triple line in 3D graph for PVT when triple point is a fixed value for all PVT? Okay, so the thing is that whatever, if you see a 2D plot, on a 2D plot, it looks like a point. So anything which will be looking like a point on 2D plot, it will be nothing but a line on 3D surface. Okay. So that is like explanation from the geometry. But physically, if we try to see, physically, basically what we are having on the, we are having actually the conversion of, we are having the conversion of three different phases. So let me just see the PPT over here. If PPT is there, then probably I'll be able to see, explain more clearly by taking the help of PVT surface on our diagram. So I think I am able to see the PPT. Can you all see my entire screen?
No, sir.
Sir, we can see it, but it is black.
PPT, can you see now?
No, sir.
No, sir.
Now is it visible?
No, sir.
So if you see in this presentation, I have shown a PVT surface, and particularly you can see below this triple point line, I have mixture of solid and vapor. Okay. So here I have solid and vapor, and if you follow above triple point line, we have nothing but mixture of liquid and vapor. So for this entire line, we are having actually, if we see immediately above, we will be finding liquid and vapor. Immediately below that, we will be finding solid and vapor. So for this entire line, whatever the combination of properties we are getting for this entire line, across this entire line, we are having presence of all three phases in coexistence. So that's why we call this as nothing but our triple point line. Okay, or triple line. Is this clear now?
So, sir, it means that there is no fixed point for triple point. Like if we vary pressure, volume, temperature to some other values according to this line, even then we will get that triple point.
No, you can
But
clearly
when we
see, you particularly follow this graph. If you particularly follow this PVT surface, you will be finding that corresponding to triple line, value of pressure and temperature is unique. Okay, so there is a unique value of pressure and temperature. The only change happening along the line is nothing but specific volume. Okay, so if you follow this particular line, the only change of specific volume is happening, and pressure and temperature are constant throughout the entire line. Is it okay?
yes, sir. Yes, sir.
So in terms of
Thank
pressure
you,
and
sir.
temperature, we have unique property value. Okay, now let me take up next question. At saturation point, we have considered value of phi as 2. So I think I have already answered this question, Ashutosh. Is it answered or do I explain again?
Yes, sir.
Okay, degree of freedom is nothing but it is the number of independent intensive properties required to specify the state of the thermodynamic system. Is it okay?
Okay, sir.
The next question is, at critical point, what is the value of dryness fraction? What will be value of dryness fraction at critical point? Can you answer? At critical point, we are saying that our liquid is instantly converting into vapor. So because of that, what will be happening? Because of that, we will be saying that we will be having entirely vapor only, so value of dryness fraction will be 1. Is it okay? At or beyond critical point, we say that liquid instantly changes into vapor. So that's why we can, though it is not a good idea to exactly specify dryness fraction, but yes, as we are having the instant transition from liquid to vapor, so we can call it as dryness fraction 1 only. Okay.
So, sir, we are just predicting it.
No, yeah, that is the only concept. Fundamentally, it is that at critical point or beyond critical point, liquid will be instantly transferring into vapor. So, if it will be instantly transferring into vapor, we can clearly say that we will be having only vapor phase. Okay.
Okay, sir.
Then next question is, please explain the dryness fraction again. Okay. Let me explain dryness, and please again explain the Gibbs phase rule for mixture of liquid and vapor. What is the so I think question number 2 and 3 I have already answered. Is it okay?
Yes, sir.
So now I need to explain question number 1.
Yes, sir. Also in question number 1, I just wanted to understand the graph part.
Okay, okay. So then let me explain only the, yes.
So why we call this AF as degree of freedom? It is totally different from the degree of freedom which we read for the gases like 3, 5, monoatomic gases and diatomic gases.
Yes, so in case of monoatomic and diatomic gases, we specifies the degrees of freedom in terms of whatever the molecular, translational and rotational motion these are having available. Okay. So there it is something different, here it is something different. So basically what we are having, the nomenclature is actually different. So wherever the concept you are referring to, name is given as same. Okay. The general idea is degree of freedom is actually used to specify that what are the number of independent parameters in general are required to specify something. Okay. So here,
Okay, sir.
so here in case of gases, that is used to specify the energy content, and in case of thermodynamic system, particularly when we are talking about Gibbs phase rule, it is actually used to specify the state of the system. Okay, so it in general it's a parameter which specifies something. So that's why it is used as degree of freedom everywhere. However, to different scenarios, its application is different. So what I was doing, I was explaining temperature and volume, and in temperature and volume, I have told that at this particular point, I'll be having complete saturated liquid. So volume corresponding to this will be Vf, and at the same condition of temperature and pressure, volume corresponding to the right side is nothing but our Vg, and the difference of these two volumes is nothing but our Vg minus Vf, which is many times referred to as Vfg. Okay. Now, if any parameter I have to specify in between the liquid vapor dome, so that parameter specific volume we get as nothing but 1 minus x times Vf plus x times Vg, and finally it takes the form of Vf plus x times Vg minus Vf, which simply we call as my Vfg. Okay, so this is a parameter, say corresponding to our some physical state of the system, where I am getting small v as my specific volume. Now this value of small v is nothing but this will be a representative magnitude of our liquid vapor mixture. Okay, so anything in this particular portion we will be having, that will be actually representing my from here to here it will be representing my x fraction. Okay, so that means how much liquid has actually converted into vapor. Now this particular line where we are having saturated liquid, so everything is nothing but our liquid phase. So corresponding to this value of x will be 0, and corresponding to this saturated vapor line, because everything is in vapor, so x will be 1, and we will be having in between number of lines which will be representing the dryness fraction from 0 to 1. Okay, so is this point now clear?
Yes, sir. And also, sir, the value of V that we calculated is an average value.
Yes.
And this average value is different from the bulk average that we calculated, right?
Yes, so what I have told you that if I have a mixture of liquid and vapor over here, okay, so this value V, whatever we are obtaining, it doesn't mean that physically it is the value of our phase, it is the value of property in our system. Physically what we are having, whatever the liquid part is there, that is having property value corresponding to this point only, and whatever the vapor part is having, that is having property value corresponding to right hand side point only. But as a number representative based on the weighted mass average, we are getting this overall property as V. Okay, so it's a number representative which doesn't specify the physical state of the matter. So we are not having any physical state of matter where we are having specific volume V. We are only having the physical state of the matter where specific volume is VL and VV, but this is weighted average, which is nothing but a combination and a number representative. Okay.
Yes, sir. And also, sir, one small doubt that I wanted to ask. In the last part of the lecture, you told us that when we don't have a specific value
Yes.
of given in the steam tables,
Yes.
we assume the relation to be linear and then
Linear.
calculate.
Yes.
For
Yes.
every entry in the steam table, we'll consider like that.
Yes, linear only. The only thing we have to consider that we cannot take very wide range. We have to choose the immediate neighboring points, and then between the immediate neighboring points, we can take linear as a approximation.
Okay, sir.
Why do we have triple line? So that is, I think I have already answered.
Yes, sir.
Okay, then I'll move to next question. It's in assignment 2, question 2. Pressure is 1.24 megapascal and temperature is 121 degrees Celsius. But in steam table there is no data. So you please don't jump into question number 2. This is related to superheated state. So in tomorrow's lecture, I'll first have more detailed discussion on the steam tables, and after that you will be able to solve this question. Okay, Vishwas?
Sir,
Yes.
Yes, sir.
sir, can we even do some questions tomorrow in the class regarding the steam tables?
Yes, we can do. Today also I have told you, na, the last question. So was the
Yes, sir.
so that is not okay.
No, sir, like I was asking like the type of questions which we have given in assignment. So like some similar kind or different questions so that we can get a better understanding of it.
Okay, I'll at least demonstrate one or two cases just first to get an idea of how to use steam table. So I'll give some random state conditions, and corresponding to that we will try to determine the value of properties. Okay.
Okay, sir. Thank you, sir.
Satyam, I have already answered, I think, this question. So is it okay, or do you once again require explanation?
No, sir, it's okay. But sir, one thing that means just now I got the confusion that you said that state postulate will be applicable for all.
So what I am saying, yes, state postulate apart from the mixtures, because where we are having mixture, their additional parameter will be required. Okay.
Okay, sir, that will be done.
I cannot relate why we require less number of parameters for more number of phases. Please explain why more phases require less. So, Vikas, let me once again answer your question. So what I am saying that when we have more number of phases, it doesn't mean that we are requiring less property. Okay. what we are basically doing when we are specifying, say, the state as saturated liquid, the meaning is that we have earlier known from our state postulate that two parameters are required. So one of the parameter has become already the physical state of the system. Okay, so the physical state of the system over here is acting as one parameter, and another parameter is nothing but the condition of temperature or pressure or specific volume or specific internal energy or enthalpy or entropy, whatever the parameter you take, that will be acting as one, and second will be nothing but your physical state of the system, because when we are referring to saturation state, we are specifying that whether we are having saturated liquid or we are having saturated vapor. So ultimately we are specifying the physical state of the system. Okay, so that physical state of the system, for example, when I told you to refer to find the saturated liquid internal energy at, say, pressure of 5 kilopascals, so you are only going to the table which is given for saturated liquid, that column only you are going to. Okay, so that physical state is also as one of the input parameter which is actually employed to locate the thermodynamic state of the system. Is this point clear?
Yes, sir. Yes, sir. It is clear, but I was asking about that formula also. In that formula, our formula is components minus number of phase plus 2. So why
Yes.
we are subtracting the number of phase? It means that more is the number of phase, less number of parameters is required.
No,
But
no. Let me tell you now. This is something which is linked with the, so this formula is particularly linked with the physical behaviors of the system. Okay. So every time you will be finding that when we are having more number of phases, components has to increase. Okay. So for example, if you are having mixture of 3 or 4 gases, so and all are in gaseous phase, so your component will be 3 or 4 and phase will be single. So it is the parameter component which will be mainly dominating in comparison to the phases in that particular formula, and that particular formula is having more relevance when we talk about thermodynamic study of the gaseous mixtures or liquid mixtures. Okay, so when we will be talking about mixtures, there the importance of formula becomes more prominent. Okay.
okay, sir.
Okay, so I think we are done with the questions which are written in the Excel sheet. Apart from this, if you have any other question that we can take up, and after that we can close this session. So is there any other
Sir,
question?
can you show a example of using steam table? I mean, a question, just a question to
Okay,
get an
okay.
idea
So
of the situation.
let me take up a question. So whatever I have discussed in the morning, is that question clear to all, or do I take up that question once again?
Sir, it was clear, but sir, another one.
Okay, another one. Okay. So let me give you all a question that I have saturated vapor state, and say it is given that the enthalpy of saturated vapor state is nothing but 1220. Okay, so we have enthalpy equal to 1220 kilojoule per kg. Now what we need to do, we need to define the value of saturation temperature corresponding to this state. Okay, so do you have steam tables with you now?
Yes, sir.
So
Yes, sir.
can you try to locate at what temperature we will be having saturated vapor with 1220 kilojoule per kg? Can you locate it?
Yes, sir.
At what point? Anyone would like to answer?
So how do we know which table to refer to?
It is clearly given in the question. We have saturated vapor state. Okay. And after that, you can refer any table. Whether pressure, temperature, everything will be not a problem. Anything can work.
So, sir, both
So
the
we don't
tables
have
would
any
be
value.
same.
Yes, sir. We
Yes,
don't
sir.
have
We
anything.
don't have
Any
any
value
value.
for 1 to 0.
So now what we need to do as per morning lecture, what I told you.
Sir, the least value is only around 2500 something.
So I have given the value only 1220, na?
Yes, sir.
So there is a 1200 value somewhere.
Yes. So what we have to do now, if you go to the table, if you carefully look into the table, you will be finding that I have 1210.7 corresponding to temperature of 70 degrees Celsius. Is it okay? Am I correct? Are you referring to saturation?
Sir, there is nothing saturated vapor state is not there. There is superheated water state. Superheated water.
Refer to very first page, 916 page number and 917. Whatever a PDF I have shared, the very first page of that PDF.
Sir, it is saturated water. It is not saturated vapor state.
It is written saturated vapor below enthalpy, you
Sir,
see.
across 70, it is 26.1 in saturated vapor.
Yes, sir. It is 2000.
Sorry. I have wrongly written it. Let me write saturated liquid. Okay. So, okay, I did a mistake. I have wrongly written it. Let me write saturated liquid. Now, can you specify? Are you able to see now the value?
Yes,
Yes, sir.
sir.
We don't have exact value, but yeah, we can.
So, what are the closest values?
275.
275 or 1210?
1210 and 275 degrees Celsius.
275 degrees Celsius.
Okay, 275. Sorry, I have written temperature also wrongly. Okay. And what is the next value?
Sir, 1235.
1235. And what is temperature?
280.
280. So it means now we require the value of temperature corresponding to 1220, which is there in between 1210 and 1235. So it means our temperature will be in between 275 and 280. Okay. So now I can take linear approximation.
Yes.
So what will be my answer then? If I say T is my unknown parameter. So what will be the equation? T minus
T minus 1220.
T minus 1220.
Sorry. Sir, T minus 275.
T minus 275 will be equal to,
Sir, we'll get 277.1.
oh, you have calculated also. Good. So give me the detailed formulation. It will be T minus 275 equal to 1235 minus,
10.7.
am I writing correctly?
1235 minus 1220.
Will it be like that or will it be 280 minus 275?
280 minus 270.
280 minus.
minus 275.
280 minus 275 divided by
1235 minus 1235.
multiplied by, what will be the value? Please tell me. Avantika, you are
20 minus 1210.
1 to
20 minus 1210.7.
okay. So
Answer
now
is temperature 279.8.
270.
9.8.
I don't think so.
नहीं सर 279.8 तो वैसे ही नहीं आ सकता ना
Yes.
कि वो हाफ कम ही होगा
Already I
It's
think,
coming 276.9.
हाँ 277 के आसपास आएगा
okay.
Yes, sir, 276.9.
Is it okay? Everyone is getting same temperature? So now tell me, are you able to, now if I give you any random question from the saturated temperature table, from the saturated state, can you identify the other parameters?
Yes, sir.
Yes, sir.
Okay, so how many are attending this session? Only you can identify or others can also?
Sir, 22 or
Yes, sir.
22.
Only 22. So out of 22, I am also actually included over here in 22. Okay,
Sir,
so yeah, please.
so to get other quantities, we have to look in the same, or
Yes,
we have to again apply the same formula. We have to apply once again this same formula to
yes.
get
Now,
another
now
quantity.
let us extend this question. Along with temperature, also calculate the internal energy for this state. So you all of you now do by your own and tell me the answer. Internal energy corresponding to this state. All of you please practice by your own and tell me the answer.
1
So the value close to 1218, this is a good means this seems to be a correct value, because what we will be having nothing but temperature is 277, so that represents the slightly higher than the mid, so the value close to 180 seems correct.
Sir, 1218.08.
Yeah, that seems correct. That seems correct.
Doing the assignments, like everything, each and everything we have to put on, right? Like if suppose steam tables question is there, then we
Yes.
don't need to write every stuff, right? We can just
No,
like write
every
by
step
using.
every step you need not to write, but you have to write over there using steam table at T1 equal to this and saturated point equal to this, your value of say internal energy or enthalpy is something, whatever you are obtaining. Okay.
Okay, sir.
Steps you need not to specify, you can simply write from steam table. Okay.
Okay. Okay.
So like we, in the previous assignment that you gave, we were ignoring the value of rho of air.
Yes.
That we have to specify at one point and then we can omit at any other next questions.
Yes, that you can do.
So the table of superheated water is not required for us.
It is required. We will be discussing tomorrow. Today we were not having sufficient time, so I couldn't complete it. Tomorrow we will be discussing about it. Okay.
Okay, sir.
Whatever I have given, whatever I have uploaded, that everything is relevant. Okay. So we will be discussing it tomorrow.
We have class, sir.
Okay. So I am now closing this session.